So C6H12O2. So when you look at the molecular formula, what I want you to do first is to get the dipole saturations, which is the number of the carbon minus half of the hydrogens. There's no halogen, there's no nitrogen, so nothing else we can do. So just add the +1. So we have a 1 degree of unsaturation. So we're going to have a higher double bond. I mean, we're going to have double bond cyclic structures. But thankfully, the ions is given. We got a peak at 1740. So what does 1740 means? That means that we have an aster, right? So this basically gives out, we have an aster in the structures, and then aster is a carbonyl. So the 1 degree saturation we need to find must be coming from the carbonyl of an aster. So there's no other information that we need to find out from here. Then we got 180 in the carbon NMR. So that means a carbonyl. So that makes sense. We got the aster, the carbonyl of the aster shows the carbon NMR. So that's the way it is. And but the remaining part, you got 50 and 40 and 30. So there are pretty much, I mean, one stands out a little closer to the ones that we may consider oxygen to it or not, depending on what it is. But most likely, because it's an aspiration, must be something has to bound to the oxygen. So one, maybe this is the one that bound to the oxygens. But we got the other two are not there. But what you need to, this one of the information that you need to get it out from here again. I told you that if there's no symmetry in the molecule, number of the carbon signal should be the number of the carbon in the structure. We got 6 carbon. If there's no symmetry at all, we are supposed to see 6 peaks. How many peaks do you see? 1, 2, 3, 4. Only 4. So what does it mean? There must be a symmetry. There must be some symmetry. What symmetry it is something that we're going to find out. But there's got to be a symmetry. All right. The proton NMR also shows these two. See here, we got singlet at 3.6. That's something that you gotta be. This must register to you. 3.6. What that means is that hydrogen, the carbon that has the carbon that has these hydrogens must have an oxygen, right? Otherwise, it wouldn't come to 3.6. So, but that's a singlet. Singlet means there's a no adjacent hydrogen, right? That's a no adjacent hydrogens. But the next part is killing because all we also have a singlet and 1.2. Share the 2 different groups of hydrogen. Even though we have a 12 hydrogen, it's only 2 groups. So what they can be? How come 12 hydrogens can be just 2 groups? So that is and this is something that probably not easy at the first time. I'm kind of spoiling for your excitement, but let me tell you some example here. When you have a methyl group, CH3, it's a 1 group of hydrogen, even though there's a 3 hydrogen, right? That just could be 1 hydrogen. So these could be singlet either of these 2. But the thing is, a 12 hydrogen, that we're talking about 4 methyl groups, right? 4 methyl groups. 1 methyl group can be that. If there's another methyl groups, cannot be the same thing, right? Unless you put it in a special way. If your carbon having a 2 methyl groups, these 2 can be identical, but these will be split by this hydrogen, right? It's a singlet. So that means that whatever the carbon is bound to shouldn't have any hydrogens at all. So this is not the situation to give out this. And then the number of the hydrogen is wrong. So if I put the butyl groups here, you can see that these 3 methyl groups are equal. 9 hydrogens are equal, and they don't have no adjacent hydrogen. So these 9 hydrogen must be singlet. And these 3 hydrogen methyl groups is also singlet. And then all together, this makes up the 12 hydrogens. So this is kind of the things that you have to get used to seeing. think about possibility of what to make of those signals and then eliminate whatever that doesn't make any sense, and then go from there. So if you got the methyl groups, we got the butyl groups, then this will make sense. We're going to have a 2 singlet. And then we have a 6 carbon to bind. So 1, 2, 3, 4, 5, and then 1 carbon of the master. So we got all the carbon here. And then we got 2 oxygen, that's definitely from the master. And then the 12 hydrogen is coming from the 3 plus 9 must be 12. So all the pieces here. Then how are we going to put it together? It's simple, right? We can put it together this way. Or we can put it together the other way. So again, even just the 3 pieces here, we may have a 2 different answer, depending on how you put it together. Which one is the right one? And then what information is actually giving the clue? So that's why this is a truly very detective story, right? You are finding, it's almost like a CSI. You are finding the evidence that narrow down to, the criminal who's making the sin. So what is the critical information to sort them out is actually this. You must have a singlet. I just got a singlet. That's a singlet, that's a singlet, this is a singlet, that's a singlet. So singlet size doesn't change. But the chemical shift, the one must be 3.6. What would be the chemical shift for this one? Being connected to the carbonyl, this one is going to be like a 2.4, right? Now 3.6. There's no way this will go down to 3.6. This will be upfield because of that's, it's not the oxygen next to it. It's oxygen the 1 carbon away. So it's going to be like a 1.5, and then this will be happening here, even for that answers. But this one will be showing like a 2.45 regions. On the other hand, if it's connected this way, methyl on the oxygens, then that's the one that's giving a 3.6 signal. And that one still can be 1.2. So that's the reason why you should pick this one as an answer, not the other. It sounds fun, right? This can be fun. Some people like this actually. Some crazy, weird people. I'm not the one though. One time I did the NMR. It takes about a week to just get the NMR spectrum. It took me 6 months to figure out what those things are. And it's not a small molecule, it's a much bigger molecules. They're like 100 carbons, maybe 200 hydrogens, and it's a way bigger molecule to figure out. But the NMR can be a puzzle. It's almost like 1,000-piece jigsaw puzzle. I don't know who likes them. I don't. But some people like it. So. And this could be a question people actually with. This is kind of what people do, solving about the structure of the protein. How many carbons the protein may have? It could be easily over 1,000, maybe 10,000, and maybe 20,000 hydrogens. And then maybe so many nitrogens, they put it all together in a different way. But you got to look at structure to find out what good drugs for that, right? So that's a structural biology, even though they're using the chemistry tool. Anyway, that's probably going to be something else you may hear later in the biochemistry textbooks. But anyway, so you get to understand, question can be very complicated. So a lot of problem solving is what you need to do at home. All right, going further, I'm going to keep posting extra problem sets. So you get to see the more question, more challenging things coming in. Now, finishing all the spectrum things, proton NMR, carbon NMR, IR, mass spec, you could expect all 4 comes together. For this question, I'm not even giving the molecular formula. Instead, I gave you the mass spectrum. So we got to figure out what it is. We have a proton NMR, we have a carbon 13 NMR, And then we don't have an IR though, but we have a mass spec. And what the question is, what would be the structure of this molecule? Right? So let's start finding out what things we have to pay attention. So look at the proton NMR, we got peaks between 7 and 8 regions, and then the two peaks. So what that could mean, that regions in 7 and 8, that's aromatic regions, typically the molecular like the benzene, structure like the benzene will show the structures. By the way, these two does not mean it's double length. These two is actually the number of the hydrogen was given as an integral. I mean, integral traces could be given, but you gotta measure that out. Actually, we did the measurement for you, and it just gives you the number of the hydrogen on the decade. So that 3 does not mean it's a triplet. These 3 means a 3 hydrogen for that peak. The integration was given as a number. So these are 2 hydrogen, 2 hydrogen. So we got 4 hydrogen in benzene. And then what else you should pay attention for this one? 2 peaks are doublet. If it shows like this, that means it's a para-substituted benzene, right? It's a para-substituted benzene. Oh, by the way, I forgot to mention these things here. The mass spec is definitely showing something we need to know. We got M, it's a molecular ion peak, and then we got N plus 2, equal height. That means you have to have a bromine. Because the bromine, 2 isotopes about equal abundance, which is a bromine 79, bromine 81. So that's why molecular ion and then M plus 2 equal height typically means that you have a bromine in the structures. So we know, so from this, we get the bromine. And then this 91, we don't know what could be 91, but that 91 peak doesn't have an M plus 2, but the middle is 91 already lost the bromine, right? The bromine, the atomic weight is at 79. So if you subtract the 79 from 170, that actually makes it 91. So the whatever the molecule, M minus the bromine, that should be this one. But anyway, from the mass spec, what we can gather is actually there's a bromine. That's the only thing that actually is significant here. All right. So we have got 6 carbon and then 4 hydrogen we found out, right? And then that's also shown by the carbon NMR. We got the 4 peaks in the aromatic regions. So that makes sense. We got a symmetry there. So these carbons the same as that, these carbons same as that. So we only got the 4 different carbons in the benzene. So that the 4 lines of the benzylic carbons, it totally makes sense along with that. But we got 3 hydrogen being as a singlet. So that must be methyl groups, right? That must be methyl groups. And then we don't know where it's going to show, but we don't know methyl. And then we can also figure things out this way. Whatever it is, the molecular ions are 170, and then you take out the bromine, that makes a 91 peak. And then that's the rest of the carbon, let's find out what those things are. What makes a 91? I don't know what's the whole thing, but we know this part. So if you find out C6H4, that weight is a 76. If you subtract this part, only remaining 15. So we found this part, we found the bromine from here. Only the resting piece is a methyl group. Methyl group is missing, and that's basically everything. And then because we already know the mass of the molecule, there cannot be anything more. So we got methyl groups, we got the para-substituted benzene, and then we have a bromine. Only 3 things to put it together. But in case, I mean, you got to make sure that that methyl groups on it shows here. That would be the makeup what makes it benzylic position. That benzylic hydrogen will show like a 2.5 region, so that totally makes sense with this chemical shape of the pig. So I know the carbonyl could put it at there too, but we don't have to consider the carbonyl because there's no way we're going to initially another carbonyl show up here. So one bromine, one methyl, we're gonna put around the benzene, and that will be all the pieces together. So that's this one. So that's pretty simple question. But just when you don't actually have a molecular formula, then you gotta think further. That will make things more difficult.